It's about time for us to get started. I think this is our 17th lecture or something like that. And today I'll collect a little later on, there's a homework 2 rewrites that are due. In addition to that, homework 3 is due on Friday. And we're going to have an exam on Wednesday. So test 1 will be on Wednesday. That's a week from today.
4th?
I think that's just right. So it's March
4th.
Thank you.
Maybe the start of the Constitution, or the first congressional session.
It covers the material the squeeze theorem. That's what it does. So that's where we are. I have given a study guide for this exam. I emailed it to people, but I also have hard copies. Does anybody want a copy of the study guide? Anybody want a copy of the study guide?
I would enjoy one. Well, I would like one. I don't want to enjoy it, but
It's okay. I mean, we do enjoy it. That's all right.
Who else? Brad, you asked me?
yes, sir.
And as I said earlier, homework 3 is due next time. I'll pick up homework 2 rewrites and more. Does anybody need a hard copy of homework 3? Okay. All right. Well, today what I want to do is I want to make sure that I want to progress through the material to get through the squeeze there, which I think I can do today. Before I get into that, there's one more announcement. I had said this off tape last time, but we're going to have a study session for this. We're going to have more than one. That's going to be on Wednesday, but the first study session I'll offer will be on Sunday. So study session for this exam. Will be on Sunday from, let's say, 2 to 4 in this room. Okay. So that's the information that I have for you. Let me go ahead and progress through some material. We had just finished what I would call a theorem about algebraic properties of convergent sequences. Okay? If you have 2 convergent sequences, you add them, they converge, and they converge to the limits, the addition of the limits. Same thing for subtraction, multiplication, and division, where the division has a little bit more provisions on it. That division property was a little bit lengthy to prove, okay, but we did it last time. What I want to move on to are some theorems about more theorems about convergent series. And here's one. It says, if x sub n is a convergent sequence of numbers, and if x sub n is greater than or equal to 0 for all n element natural numbers, then the limit as n goes to infinity of x sub n, whatever that is, so we know it converges, that's going to be greater than or equal to 0. And we can call that number x if we want, and I will. So then x equal to that limit is going to be greater than or equal to 0. Audra, this is an easy to understand statement. It's saying, hey, you got a sequence that converges, and all the terms of the sequence are positive. What it converges to has to be bigger than or equal to 0. You can't converge to something negative. That's what it's saying. So check the proof of this guy is is by contradiction. I'm going to do what the book does here. Okay. So so in contradiction, we suppose the if part. So suppose x of n converges. And if it converges to something, to x, and x of n's are all greater than or equal to 0. That's true for all greater than 0. For all n element natural numbers.
Wait. Why do we have greater than 0? Shouldn't that be less than 0?
Well, here it's greater than or equal to 0 for the x of n's. And it is greater than or equal to, I should say that. Okay. And that's for the x of n's. The x itself is going to be assuming the opposite for the contradiction, Corey. And that's to do with the x. We will assume, or suppose, and x is less than 0. So let me stop for a second. Remember, by contradiction, you suppose the if part. I'm supposing the x of n converges. So if it converges, it converges to x. And that part of the if part is that each term of the sequence is greater than or equal to 0. We're supposing that. To prove something by contradiction, instead of assuming, or to prove something by contradiction, we assume the opposite of what we want to show, opposite of what is. So here, we want to show that x has to be greater than or equal to 0. What it converges to has to be greater than or equal to 0. Suppose the opposite. Suppose x is less than 0. And then we're working with that supposition in hopes to get a contradiction. And the only thing we've assumed that we're not supposed to assume or have any type of control over what we assume is that x is less than 0. So if we get a contradiction, this was wrong. Okay? That's what we're working. Okay, well, if x is less than 0, then here's what I could say. There exists a k element of the natural numbers. I guess I should say why I'm about to write down a mistake. So let's back up. What do we know? We know x of n converges to x. So since x of n converges to x, that's the way I'll write down the convergence. That's the way I'll symbolize it this time. Okay, so here's what I'm thinking. What I'm thinking is that if x of n converges to x, then no matter what positive number somebody gives me, there's some point in the sequence, we call it k, such that from that point on, n greater than. Okay. All the terms of the sequence, their distance from x is going to be less than whatever positive number was given to me. So the positive number I'm going to pick is minus x. Because x is, we're assuming x is negative. Okay, so minus x is positive. So here's what I'm going to do. So minus x is going to represent my epsilon. My epsilon is going to be minus x. What I'm going to say is, there exists a k element of natural numbers such that for all n bigger than or equal to k, the absolute value of x of n minus x will be less than minus x. So, for all n bigger than or equal to k, if we rewrite this statement, and this looks a lot like one of the homework problems that's in homework 3. If we rewrite this statement, what we get is that x is going to be less than x of n minus x, which is less than minus x. And solving for x of n, okay, this inequality that involves absolute values can be translated into this compound inequality by a theorem we've been using. So for all n greater than k, if I solve for x, sub n, I'd add x to both sides. So 2x is less than x sub n, which is less than, and here if I add x to both sides, what would I get?
0.
Okay. And right here, this is a contradiction job. You see, we're assuming all the x sub n's are non-negative, greater than or equal to 0. And right here, we're saying, well, look, the x sub n's have to be less than 0. That's a contradiction. X sub n's must be greater than or equal to 0. So we must have assumed something wrong. We didn't make a mistake in our logic. And so what we assumed that we had some control over, that must be wrong, is that x was less than 0, so it must be the case that x is greater than or equal to 0. And that concludes this proof. Any questions about that? Okay. Well, we're going to use this theorem to prove something else. So here's another statement we're going to look at. So if x sub n and y sub n are two convergent sequences, with, or such that, x sub n is less than or equal to y sub n for every n number of natural numbers, then the limit as n goes to infinity of x sub n is going to be less than or equal to the limit as n goes to infinity of y sub n. Okay, that's what we're going to work on next. What the heck does this theorem say? Chuck, know what this theorem is saying? It says, look, you got two convergent sequences. You got two convergent sequences. And it turns out that term by term, each comparison, what's in the fifth place of x sub n and what's in the fifth position of y sub n, it always, the x sub n's term is less than. Okay? For each position, not just the fifth, but for all of them. Okay? Then whatever x sub n converges to, it's got to be less than or equal to whatever y sub n converges to. That's what this is saying. Okay. So here's my proof. We're going to let x sub n converge to y. Converge to x, and we're going to let y sub n converge to y. Suppose, to meet the criteria of the definition, that x sub n is less than or equal to y sub n for all n element natural numbers. What do we want to show? We want to show that x is less than or equal to y. That's what we want to show. All right. You know, the previous theorem, the thing we've already shown today, it said, hey, look, if all the terms of the sequence were non-negative, and it converges, then what it converges to, it has to be non-negative. Okay? Well, I don't see necessarily a non-negative sequence in what we're working with, okay? But we can create one out of what we're working with. And the reason I can create one is that I know that the x sub n's are less than or equal to y sub n's for each n. Okay? So what I'm going to do is we're going to consider a sequence that's an algebraic combination between those two sequences. Namely, we consider the sequence that is x sub n, that is y sub n minus x sub n. Okay. Now, since x sub n is less than or equal to y sub n for all n in the natural numbers, then that means that y sub n minus x sub n is going to be greater than or equal to 0 for all n found in the natural numbers. So this sequence here is a sequence, y sub n minus x sub n is a sequence, and all of their terms are non-negative. It's the right thing to say. I usually say positive when I'm not being so careful.
Because we have to consider 0.
Oh, we have to consider 0, that's right. So, so we're looking at this non-negative sequence, and since x sub n converges to x, and y sub n converges to y, then that algebraic property of convergent sequences theorem can kick in. That is, x sub n minus y sub n as a sequence, what's it going to converge to? I didn't write it down correctly. The y sub n minus x sub n, which is what we're looking at. As a sequence, what's it going to converge to?
Y minus x.
That's right. Okay. By the previous theorem, if you take a sequence that all has non-negative terms, what it converges to has to be greater than or equal to 0. Is that okay with everybody? So that says y minus x has to be greater than or equal to 0. So that means that y had to be greater than or equal to x. And that's the proof. We've shown that x is less than y, or y is bigger than x. Bigger than or equal. Is that okay with everybody? Makes a lot of sense. I mean, you got one sequence that's always bigger than the other one. Both of them converge. What the bigger sequence converges to has to be bigger than or equal to the little sequence. That's all it's being said.
Question.
Go ahead, John.
If we replace the less than or equal to with strictly less than, and then strictly less than again with the limits, would that still be true?
With the limits. No, it's not.
necessarily.
You can find a sequence that says that one term is always less than another term, but what they converge to might be the same. So you'd have to have this equality.
Okay.
But if you had switched this to just strictly less than, okay, you would still have to have less than or equal to.
Thank you.
Thank you. I'll show you a quick example.
Okay.
So here, if you say y sub n is equal to 2, and x sub n is equal to 1 over n.
Okay. I see.
Which one's bigger all the time?
Y sub n.
Right, it's double this guy every time, okay?
But they both converge to 0.
But they both converge to 0. That's right. So we don't have just the strict inequality being held.
Okay. That makes sense.
That's good. Anybody else with a question or comment? On the study guide, I have said to expect certain types of problems, and some of them are true or false questions might be there. And the question John just asked is a question that I could ask you, that type of thing.
Sorry, guys.
I won't ask you that question. But that's something that, where you think about it and say, wait a minute, can this happen? And you look through examples or think back to theorems and facts that we've had, definitions, to say, well, it can't happen because of this. Here's another statement that I want to cover, and it's the last one before the squeeze down. So this theorem says, if x sub n is a convergent sequence, if A is less than or equal to x sub n, which is less than or equal to b, for all n element natural numbers, then A is less than or equal to the limit as n goes to infinity of x sub n, which is less than or equal to b. What is this saying? This is saying, hey, look, if you've got a convergent sequence and all the terms of the sequence are between these specific two numbers, then whatever it converges to has to be between these two specific numbers, inclusive. Okay? That's what's being said. Remember what we just proved was if you got two convergent sequences, one was always smaller than the other one, or less than or equal to the other one, then what they converge to has to be less than or equal to each other. Does that make sense? And that's what we're going to use that previous theorem to prove this guy.
So A and B kind of, or can kind of act as our upper and lower bounds for the.
Yes, they are. And not only that, we can think of them as sequences too. We can think of them as constant sequences, and that's going to be what the proof is based on. So here we're going to let x of n. Okay, look, we need it to be a convergent sequence. If it converges, that means it converges to something. Let's call it, or give it a name. Let's give that limit a name. Let x of n converge to, tell them what you think we should call it. X. That's a good answer. Converge to x. And suppose, there's something else I got to suppose. What else do we have to suppose here? Suppose, what else is in the conditions here?
That x sub n is sandwiched between A and B.
That's right. That's right, for all n element natural numbers. And what is it we want to show? We want to show that A is less than or equal to x, which is less than or equal to b.
So do we not need to repeat the for all n in the natural numbers for the conclude or for the part that we're trying to prove?
No, because this doesn't depend on n natural numbers. This is a fixed x, so that's a fixed number that's converging. No, we don't. Those of you who don't know, Alabama won their basketball game last night. Alabama's basketball team is not any good. I don't think I've mentioned Alabama sports to you this term, so we'll take 1 second to take Alabama sports. Alabama's basketball team is not any good. Yes?
I do believe we did mention Ohio State football to you, though.
You did? Okay. I'm glad you brought it up again.
Okay.
They played well. This one, I think Ohio State played well. That's why they won that championship.
Yeah.
They played well. Good for them. We wanted to win that championship, so we're not thinking anything bad about a team wins the national championship. We're thinking that's what we wanted to be. Good for you guys.
These are close, though.
You can't win it all the time. When you do win it, enjoy it because it doesn't happen all the time.
That's very true.
So if you're pulling for Ohio State and you see you won that championship, enjoy it. It doesn't happen. It's good to have a good time. You should bring it up every chance you get. Go ahead.
Sorry, I apologize.
Anyway, Alabama's basketball is so bad. They think of any type of little advertisement for a way to get more people there. And so last night's advertisement for to get people in the arena was they called it Star Wars Night. So any child who came with their parents who was dressed up as a Star Wars character got in free, I think. That's what they did. Just to help get people in the arena. And so they asked, they realized that it wasn't clearly defined. I mean, what does child mean? And so they said anyone under 50 with their parents that's dressed up as Star Wars. They get it. Okay, we're working on this. Okay, here's what I'll say. I'll say consider the sequence which is a constant sequence. And converges to, what's it converge to? That's the problem. Since for all n element natural numbers, we have x of n is less than or equal to b, and x of n converges to x, and the sequence is b converges to b, then by the previous theorem, the limit of the x of n's is less than or equal to the limit of the constant sequence that's b. So what do we get? We get, what's the limit of x of n's? What are we calling it? Is less than or equal to b. Okay, we did it that direction. That's one of the inequalities. Well, we're going to do the same dang thing for the other direction. Instead of considering the constant sequence b, we're going to consider the constant sequence a. Which converges to a. Since for all n element natural numbers, a is less than or equal to x of n, and each one of these converges sequence, then by the previous theorem, whatever this converges to is less than or equal to whatever this converges to. So we have a is less than or equal to x. So combining these two inequalities, we have a is less than or equal to x, which is less than or equal to b. That concludes that. We can get a little better than this. So what this theorem said, hey, look, if the terms are sandwiched in between, all the terms are sandwiched in between two numbers, and the sequence converges, then what it converges to has to be sandwiched between those two particular numbers. That's what it says. But what happens if we've got three sequences involved and they're not all constant, and we have some kind of relationship? So here's the squeeze theorem. Boy, it's a beautiful name theorem. That's a great Scrabble word. It is. You use all your tiles. Man, oh man. Put that on the board. It says, suppose that x of n, y sub n, and z sub n are sequences. The book always says sequences of real numbers, which is important because you can have other types of sequences. You have sequences of functions. But here, we understand these sequences, real numbers, that's what we're talking about. Such that x sub n is less than or equal to y sub n is less than or equal to z sub n, and that's true for all n element natural numbers. And we're also going to suppose that the limit as n goes to infinity of x sub n equals to w, which equals to the limit, oh yeah, as n runs to infinity of z sub n. Then, this is a conclusion. The limit as n goes to infinity of y sub n, that's going to equal to w as well.
So all three sequences are converging to the same.
They are. They are. And that's part of the conclusion. Half or 2/3 of the assumptions involved in what you just said too. So let me repeat just a second. What are we proving here? What we're proving is the following. You got three sequences. Smallest, middle, biggest. Okay? You're assuming that the smallest and the biggest ones converge, and they converge to the same thing. They're going to force the middle to converge to that same thing. Is that okay? I want to tell you, if the smallest converges and the biggest converge, but they don't converge to the same thing, it doesn't mean that the middle one is going to converge at all. They might bounce around in there. But these guys are converging to the exact same thing. They're squeezing what the x sub n, the middle guys, what the y sub n, the middle guys have to go to. They're squeezing y sub n to a certain number. That's what's happening. Okay, let's do the proof. We've got about 15 minutes, 17 minutes. So we're going to let x sub n, y sub n, and z sub n be three sequences, or B sequences. Such that x sub n is less than or equal to y sub n is less than or equal to z sub n, and that's true for all n L natural numbers. And the limit as n goes to infinity of x sub n equals to the limit as n goes to infinity of z sub n, which is some number w. And what is it we want to show? We want to show the limit as n goes to infinity of y sub n equals to w. Well, how do I show that a sequence converges? I'm trying to show y sub n converges. How do I show it converges to a specific number? All right, that's what we're going to do. We're going to let epsilon be greater than 0. What do we need? That's right, we need a k. That's a spot sequence. So it's a natural number such that for all n bigger than or equal to k, the absolute value of y sub n minus w will be less than epsilon. That's what we're doing. need a second, I don't think about it. The book has the proof, okay, we can look, but I'm gonna take just a minute. What would I do? How do I prove this? So you're a person, I'm a person too. Well, I'm facing this problem. What do I do? Well, I think I would use that x sub n and z sub n that goes go to w. I think that's something that's important. So here I'm going to say since the limit as n goes to infinity of x sub n equals to w, then there exists a case of one element of natural numbers such that for all n bigger than or equal to the case of 1, x of n minus w will be less than epsilon. Okay. Similarly, since the limit as n goes to infinity of z sub n equals to w, then there exists a case of 2 element of natural numbers, such that for all n greater than or equal to case of 2, z sub n minus w will be less than epsilon. Well, maybe having both of these things happening would be a good thing. For both of them to happen, what am I going to do?
Let k equal to max.
All right, so let k equal to the max of case of 1 and case of 2. Then, for all n bigger than or equal to k, we have two things. We have absolute value of x sub n minus w is less than epsilon, and the absolute value of z sub n minus w is less than epsilon. What I'm going to do next is I'm going to write down those two statements as inequalities, but they're not going to have absolute values. And I know I can do that by a big fact we've been using a lot, having to do with inequalities involving absolute values and translating them into inequalities that don't have absolute values. So for all n bigger than or equal to k, here's what I have. The x sub n statements will translate into, we have minus epsilon is less than x sub n minus w, which is less than epsilon. Is that okay with everybody? And minus epsilon will be less than z sub n minus w, which is less than epsilon. That's what I got. So for all n greater than or equal to k, really the first part of this thing, I want to work for all n greater than or equal to k, but what I'm about to write down is true for all n. Okay? We have x sub n is less than or equal to y sub n is less than or equal to z sub n. That was a statement that's part of the conditions of the theorem. Okay? Now what I'm going to do is I'm going to subtract w from each part, which implies x sub n minus w is less than or equal to y sub n minus w, which is less than or equal to z sub n minus w. Okay, so this is really a true statement for all natural numbers, but I'm just concentrating on the ones that are bigger than or equal to this k. And I'll put a period here. Period. So for all n bigger than or equal to k, we have, now this statement isn't true for all n's. It's only the ones bigger than or equal to k, or we're sure for those. We have minus epsilon is less than x sub n minus w, which is less than or equal to y sub n minus w. which is less than or equal to z sub n minus w, which is less than epsilon. Okay? So, let me get kind of out of the way here. And to say, what we used here is right here. So I just rewrote the above inequality right here. But I added some parts. What I added came from here, minus epsilon is less than this part, and from here, z sub n minus w is less than epsilon. Okay? So for those two parts, what I added. And if we take away a lot of the, or some of the quantities involved there, I can gather out of that last compound inequality the following.
Minus epsilon is less than y sub n minus w is less than epsilon.
That's correct.
And that's true for all n greater than or equal to k. Now, if we translate that into a statement that involves absolute values, what will we write? This would say the absolute value of y sub n minus w is less than epsilon. Okay, that's what it says. So, that means the limit as n goes to infinity of y sub n equals to w. That's the proof. That's a proof of this. Anybody have a question about that?
Do we have any examples of something like that?
Yeah, we sure do. We looked at something. So that's how much I had prepared. And so now we're going to make up an example. Yeah? So wait just a second. I want to think of something. Okay? Okay. Show the limit as n goes to infinity of sine of n over n equals to 0. I can do that. So here's the proof. So the first thing I'd note is that for all n element natural numbers, if I look at sine of n, well, sine of n is a number. You get out a number. Okay? And what are the values of sine run from?
Minus 1 to 1.
That's right. Okay? So here, definitely it's going to be in between minus 1 and 1.
So it's bound.
It's bounded by those two sequences. Well, I'm sorry. It is bounded by those two numbers. Yes, sir.
But it also by those two sequences.
Yes, that's right. I was that's okay. Didn't mean to say that.
I understand.
What I wanted to say is these two sequence bounded. So, look, I started with sine because I knew I could get bounds for it. But sine is not the actual term of the sequences that we're looking at. Really, the terms of the sequence we're looking at is sine of n over n. So, from the previous inequality, so for all n element natural numbers, to say, minus 1 of n is less than or equal to sine of n over n, which is less than or equal to 1 over n. Okay? So this is like my x sub n from my squeeze theorem. This is my y sub n, and here is my z sub n. Is that okay? And so what I try to do in this problem is create a problem so that I can find two sequences that bound the sequence, one smaller, one bigger, but yet I have to make sure that the outer extreme sequences converge to the same thing. What do the outer extreme sequences converge to? What's that converge to?
Yes, you do.
And what's 1 over n converge to? Okay. Thus, by the squeeze theorem, sine of n over n converges to 0. Oops, that's the example. Beautiful, Corey. It's good to show an example of something, especially something we use in squeeze theorem. We got a name to it. I don't know if it gets a name. So that's an example. Good. That concludes the material that I'm going to have on test 1. I'm going to do one other theorem, but it's not going to be on test 1, but I'm going to go ahead and move forward. Unless there's a question about something we've done. Anybody have a question about anything? Okay, let's do one more theorem. That'll be it. And on Friday, you can ask anything you want. Let me stop this for a second. Maybe I don't know. Does anybody want to ask anything about homework 3? Anything?
I'll bring a question on Friday.
Okay. Anybody want to ask anything? Okay. Well, then let's do one more theorem. And then we'll call it quits. You know, the people who aren't here, who are watching this on videotape, are saying, ask a question. That's what they think. Don't let it go on, I think. I'm making up things, but that's what I would be thinking. Somebody ask a question. Here's the theory. It says, let x sub n converge to x. Then, the sequence, the absolute value of x sub n's, they converge to the absolute value of x. So let's let x sub n converge to x. We want to show the absolute value of x sub n as a sequence converges to the absolute value of x. So I want to show that a sequence converges. And how am I going to show a sequence converges? What's the standard setup? What's the first thing I'm going to write? That's right. What do we need? That's right. We need k element natural numbers so that something happens. We just got about a minute. That's all I need. K element natural numbers such that for all n bigger than or equal to k. Now here's where we have to be careful. Remember, I want to show the absolute value of x sub n is converged to the absolute value of x. So I write down the absolute value of absolute value of x sub n minus the absolute value of x is less than epsilon. Here's something to note. So that's what I want to show. No, this absolute value of x sub n minus absolute value of x, all inside absolute value, is less than or equal to the absolute value of x sub n minus x. This is something we proved. It is something we proved a good while ago. It was a corollary of the triangle inequality. I can prove it again, but it's something we did prove, okay? So look, I want this guy right here, this left-hand part, to be less than epsilon. But I know this guy's less than this. So if I can show this is less than epsilon, I'd be in good shape. But wait a minute, I can show this is less than epsilon because I know the limit is n goes to infinity of x sub n equals to x. So I can make this be less than epsilon. So that's going to be true. So since the limit as n goes to infinity, come on man, almost caught it. Oh my gosh. The limit is x sub n, as n goes to infinity of x sub n equals to x. There exists a k element of natural numbers such that for all n greater than or equal to k, the absolute value of x sub n minus x is less than epsilon. So for all n greater than or equal to k, the absolute value of x sub n minus the absolute value of x will be less than epsilon. It's just based on this relationship, okay? And that's a consequence of the triangle inequality, and we did it. All right, that ends today's lecture. I need to get homework from you, I think, rewrites. And we'll see each other on Friday. Don't forget, we're having a study session on Sunday, 2 o'clock in this room.